Hello. Today we're going to talk about spheres. We're going to cover both surface area and volume in the same section. Previously we separated them. For spheres we'll do both at once. And spheres, notice they get their own separate section, and they deserve it. Spheres are important. By the way, if you hear anything in the background, it won't stop raining. For days now it's been raining. So I just have to do it out here in the rain. Well, first, like everything else, before we can talk about spheres, and I haven't even defined a sphere yet. Well, just like with a circle, where it's the set of all points equidistant from a given point in a plane, a sphere is just a three-dimensional analog of that. In other words, a sphere is all the points in three-dimensional space which are equidistant from a given point, and that point is called the center, and that's right there. Okay, now we know what a sphere is. What about this other stuff? Well, this is a chord, just like with a circle. It goes from one point on the surface of a sphere to another. That's a chord. This is a radius, just like it was with a circle. And in fact, we used that term for regular n-gons too, didn't we? Hexagons, pentagons. Very common term. Well, we use it for spheres as well as circles. And this here, this is a chord, but it goes through the center. Remember what we called that for a circle? Well, we call it the same thing for a sphere. That's still the diameter. So this line here is the chord. This is the radius. It's the diameter. It goes through the center here. Surface area, well, that's just the whole outside part of the sphere, you could say. In other words, the set of points which are equidistant, just those points and not the interior. That is the surface area of the sphere. And this right here, right through the hidden lines in this thing, this is a plane cutting the circle right at the center. And there are lots of ways to do that. In fact, there are an infinite number of ways to do that, because we can take this plane and tilt it any way we want. As long as we rotate it about this diameter, it'll still go through the center. And it will still produce what's called a great circle, as opposed to a mediocre circle. If it cuts through the center, it's called a great circle. However, if we cut this sphere with any plane at any angle, we will still get a circle, but it'll be one of those not so great circles. This great circle happens to be the biggest circle you can produce. If you cut the sphere with a plane, you will always get a circle, but if that plane doesn't go through the center, every other circle you can get will be smaller than the one that goes through the center. If you think of it that way, it might be easy to remember that it's called a great circle. Spheres are important. They're one of the things that, of all the figures we've studied here, most of them don't turn up in nature that often. Although crystal structures do have n-gon shapes, like hexagonal, cubic, things like that. The stuff you see just walking around, you don't see too many of the types of figures that we've studied, except for man-made structures. Spheres occur in nature all the time. If you ever get to, in fact, if you go on YouTube, I'm sure you could find a slow motion video of water dripping from a faucet. It'll start out in a teardrop shape as it separates from the faucet, but as it falls, it'll contract into a sphere. A sphere has the smallest surface area for a given volume. In other words, if I were to produce a cube, a pyramid, a cylinder, any polyhedra, or one that's just three-dimensional, doesn't even have to be a polyhedra, which of course a sphere isn't, or a cylinder. Anyone you can come up with the same volume, will have more surface area than the sphere. In the entire universe, there is nothing that will produce a smaller surface area for a given volume than a sphere. And that's the reason, they'll explain that to you in science class, the water drops will form spheres as they fall. Because water isn't just a blob of stuff like in a glass. It's not just a blob. It actually has surface tension. That tension doesn't exist below the surface, but at the surface there's something called surface tension, which is when things drop into water, the surface produces, well, the molecules at the surface try to stick together. That's why, if you're really careful, you can float a metal pin on top of water. Metal doesn't float, and there's no way in the world that a pin should float on water. But if it doesn't break the surface tension, it can just sit there. If you put it in point first and then let go, it'll drop straight to the bottom. But if you're real careful, you can try it. You might get a pin to float on top of water. That's also how wasps can stand on water. They just don't break the surface tension. If they try to stand on water that's got some soap in it, soap tends to break the surface tension. If they do that, they'll sink into the water. And that's another experiment you can try. If you've got a slow motion camera, try dripping regular water and then drip soapy water. And see how quickly, relatively quickly, they form spheres. The soapy water might not form a sphere at all, I'm not sure. Regular water turns into a sphere because that minimizes surface tension. You minimize the surface, you minimize the surface tension. As you study science, you'll find tons of things that work that way in nature. They automatically move towards a configuration of lower energy, lower tension. Usually, they minimize something. You just have to figure out what it is they're trying to minimize, and you can frequently predict what's going to happen in any natural reaction. Well, so much for the science end of it. That's one reason that spheres are important. So what about spheres in mathematics? Well, we've got surface area, and let's call that A sub S. And I'm not going to prove this. In calculus, it's pretty easy to start with a circle and prove that if you take that circle and spin it around the diameter, that shape you produce as you spin it will be a sphere, and the surface area will be exactly 4 times the area of a circle with the same radius. In other words, 4 pi r squared. Just remember, it's 4 times the area of a circle with the same radius. That's the area of the surface of the sphere. For the volume, it's a little bit different, but not too bad. It's 4/3 pi r cubed. If you can remember this one way you can always remember to get the surface is to, if this works for you, it might be easier to just remember the formula. But if that doesn't work for you, if you can remember this one, remember that if you take the 3 out of here and turn this into 4/3 pi r squared, in other words, move the 3 out and drop this down 1, you get 4 pi r squared. When you get to calculus, what I just did might make a lot more sense to you. At this point, it might just be an easy way for you to remember this one if you can remember this. If not, then remember this one, and remember you just add some 3's to it. In other words, for volume, you change the 2 in the r to a 3, and then you divide everything else by 3. So the 2 changes to a 3, and then you divide by 3. Either way you look at it, going back and forth between surface area and volume, you're going to throw in or take out some 3's. Or on the other hand, you can just memorize both formulas. Whatever works for you. Now, before we work the problems, recently, you can Google it, in Scandinavia, I think maybe it was Finland, spheres, perfect spheres of ice washed up on the shore all over the place. What happened was it was so cold that as the waves rolled up, the foam froze, and it froze in such a way as to minimize surface tension, so they found these perfect spheres of ice lying all over the beach. Google it. I'm sure there are pictures up there. It's pretty cool, and it gives you an idea of what happens in nature. Spheres tend to spontaneously happen on their own, and it's pretty much all because of surface tension. Otherwise, there would be no particular reason to try to minimize surface area. Well, enough of that. How about the approximate radius of a sphere with surface area 32 pi square meters? Well, this is easy. All we have to do is lay out our formula, if we remember it, and of course we do. It's 4 pi r squared equals 32 pi. Now, I think the first thing we can do is just divide through by pi, and you get 4 pi r squared equals 32. Well, 32 divided by 4 I think is 8. So r must be the square root of 8, which is 2 times the square root of 2. That's what I get. Well, my calculator says this is 2.828, which looks a lot like that one. So the answer over here would be B. And this was real easy. Just had to remember your formula for surface area of a sphere. The rest is just algebra. Well, let's see what went wrong here. Surface area is 4 times the area of a circle with the same radius. 4 pi, well, we got that right, 4 pi r squared. The radius is 5, so that's 4 pi 5 squared. Everything almost makes sense. Let's see what they said here. Find the surface area of the hemisphere. Oh, wait a minute. Hemisphere? Well, hemisphere is half of a sphere. That's kind of a giveaway. That's why they put the hemi in front of it there. So, all you need to do is divide this by 2, because the surface area of the hemisphere would be half of the sphere. That's what it means. Hemisphere is half a sphere, so the surface area is half that. So that should be really 50 pi. And this is like 157 something. So this is actually a pretty simple mistake, easy one to make. You lay out your formula knowing that that's what you're going to use, and then forget that you're not really looking for the whole sphere. You only want half of it. I used to make mistakes like that all the time on tests. I quit making those kind of mistakes when I quit taking tests. Well, looks like another mistake. Wow. I'm guessing Inseam and Fleabite have been hard at work, getting things wrong all over the place. What's wrong with this one? Maybe they didn't get it wrong. Maybe they got it right. Just because they say it's wrong, how do we know? Let's take a look. What did they do wrong in finding the volume of a sphere with diameter 8 feet? Well, let's see. Diameter 16 feet. Okay. Radius would be half of that. That's 8 feet. That looks good. 4/3 pi r. Oh, wait a minute. 4/3 pi r cubed. Well, that's a mistake. This should have been a 3. So I bet if we just multiplied this by 8, I mean, the difference between 8 squared and 8 cubed is 8, right? 8 times 8 squared is 8 cubed. So you get everything else right. If we multiply this by 8, which would be the same as multiplying this by 8, you should get the right answer. And if we multiply this by 8, that's just throwing another 8 in there to turn this into 8 cubed, we get 2144.64. And due to round off error on somebody's part, most likely mine, we can compare that to the regular answer and find that we're off by 2 100ths over here. I'm sure that's just round off error. This is in fact correct, and this is correct. Notice we get the same thing. Now here they'd like us to show, demonstrate, find the relationship between surface and volume and radius. And let's take a look at the two equations and see what anything jumps out at us. We get 4 pi r squared. That's the surface area of the sphere. On the other hand, 4 pi r cubed over 3 is the volume. Well, let's see here. That means volume. If we started with surface area, we could get the volume by multiplying by r. That would give us our r cubed, kind of like what we did in the previous problem when it was set up incorrectly. Now that's s times r over 3. And that is the volume. Or you could say that surface equals 3 times the volume over r. Those are both legitimate ways to relate volume and surface. Here they laid it out all in terms of volume on the left and some expression including surface area and radius on the right. So this is the one we'd be looking for here. Do we have that over here? There we go. First one up. V equals RS over 3. V equals SR over 3. Okay. The answer is A. All we had to do was lay out our two formulas for surface and volume and figure out if we could pull one out. And we did. Surface is, in a sense, contained in this one because we have 4 pi r squared inside here. We just write this as r squared times r and then divide by 3. So this was actually pretty easy too. And here we just have to figure out a couple of things. They actually gave us everything we need to answer the problem or answer the question. But it's not immediately obvious, is it? And let's see here. We've got a sphere inscribed in a cube of volume 64 cubic centimeters. Well, I think we'd be better off if we knew the side lengths. Well, what would the side lengths be? Well, I think the cube, since we have a cube, one side length to the third power, or cubed, should be 64. Well, 4 cubed is 64, right? 4 squared is 16 times 4 is 64. So we have that s equals 4. What does that tell us? Well, if this thing is inscribed in this cube, then the distance from here to here across the sphere through the center, in other words, the diameter for the sphere, equals 4. So r equals 2. And all they want is the surface area. Now we have r. There's only one parameter for a sphere. That's the radius, just like with a circle. So all we have to do is plug 2 into our formula, which is 4 pi r squared, which is 4. 4 times 4 is 16. So we get 16 pi. Oh, and they put the answers in terms of pi. That was nice of them. So it's 16 pi. Now that's C, and of course this was in square centimeters. Again, very easy as long as you remember your formula for the surface area of a sphere, and don't forget the volume of a cube is one side cubed. Considering you use the same word on both sides of the equation, might make it easier to remember. Volume of a cube is the side cubed. Here we're working backwards again. We've done this many times before. These backwards problems are always just a matter of remembering your formula. In this case, the formula for the volume of a, well, balls are spheres, usually. Unless it's a football. But everything else that I can think of. In fact, beach balls, that's one of the naturally occurring spheres in nature. Without beach balls, you couldn't have beach movies. Very important. And other balls that I can think of. Baseball, bowling ball. Think of them yourself. Try to figure out. Other than football, let's see, soccer balls are spheres. So we're just going to have to assume that by ball, they mean sphere. And not a football. And that means that we use our volume for a sphere. 4/3 pi r cubed. And that is, wow, big number, 1427.54. Now this is easy. We can write that r cubed, multiply through by 3, divide through by 4 pi, and we get 3 over 4 pi times 1427.54. So, for a radius, after we plug some numbers into our calculator here, and when I'm doing this, I frequently just replace 3/4 with 0.75. It's such an obvious and even fraction. For instance, 4/3, that's 1.33333 and goes on forever. If you don't want to get round off error, then you multiply by 4 and then divide by 3. But 3/4 is a nice even 0.75. It's easier to punch into your calculator than times 3 divided by 4. So I just always convert 3/4 to 0.75. When we do that, we get the cube root of 340.84, or 6.985. And you could round this to 6.99, I guess. Now that we have the radius, and they gave us the volume, well, let's see here. We could use, certainly, now that we have the radius, we could of course use our 4 pi r squared. Or, just for fun, we could figure out the surface area just by knowing the volume and the radius without actually using the surface area equation. Remember that one? We had that just in a previous problem. We had that S times R over 3 equals the volume. Well, so we can write that our surface area, which is 1427.5, that's not the surface area, that's the volume. .54, pardon me, is S times, say, 6.99 divided by 3. Or, this would imply that S so if we use this formula that we figured out in the previous problem, we get 612.678. And suppose we did it the other way. Here's where we found the radius. Here's where we used this equation. to find the surface area. Suppose we just use our 4 pi r squared, where r is right over here, 6.99. What do we get? Now that's 4 pi times 6.99 squared. And if we do it the other way, and once again we're off a few hundreds here because of the round off. I know this number looks different, but really if you round this off, well actually you round this off at 613, you round this off at 614. I admit I don't like that large a difference, but maybe I should have used 6.985 here. When you divide by numbers, the change down here usually has more effect than the one up here. You learn a lot more about that in college if you go on to study things like numerical analysis and figure out what kind of error you generate when you've got an error in the denominator as opposed to the numerator. When you've got small numbers, relatively small numbers in the denominator, small errors can produce big errors in the final result, or at least bigger. Other than that, I don't really understand why there are 200s difference, because it's easy to see algebraically that these are exactly the same equation. It could be my calculator. Maybe my calculator just preferred this one to this one. I think this is probably more accurate. Well, there's a spherical ball I forgot to mention. Tennis balls. Yeah, pretty much spherical. You got that little, not sure what that is. It's a white line that goes through a tennis ball. Very similar to the threads on a baseball. About the same pattern anyway. And the rest of the surface on a tennis ball is actually kind of fuzzy. At least all the ones I ever used were. So I don't know if they're including the fuzz in the circumference, or if that's what the circumference is after you smash it down. If you don't play tennis and you're wondering about that, the fuzz on there helps the tennis ball grip or grab the strings on the racket, or look at it the other way, the strings on the racket grip the fuzz. That allows you to put spin on the ball fairly easily. If you hit the ball, say, with a backhand side stroke, you can put side spin on it. With a forehand, bringing it up, you'll put top spin on it, which will cause the ball, after it hits the ground, to move forward much faster than it normally would, and lower. The fuzz also helps the tennis ball catch the air and cause it to curve in mid-flight if you hit it right. It's actually pretty easy. I couldn't throw a curveball to save my life, but I can make a tennis ball curve in mid-air pretty easily. It's not that hard to do. They curve pretty easily. I believe that's all the fuzz on the surface. It catches the air and causes the ball to change direction if it's spinning enough. Well, that's your tennis lesson for the day. Now, what about mathematics? It says here they're stored in a cylindrical container, alright, with that height and that radius. First thing I want to know is the volume of a tennis ball. Okay. They gave us a circumference. That's the same as a circle. 2 pi r. They didn't give us r, but they gave us c. So we just have to go backwards and get that r equals c over 2 pi. So once we have the radius, we just plug it into our 4/3 pi r cubed. I get about 2.064 for r cubed, and this works out to 8.641. And of course, when there are pi's and numbers that have been rounded off that are cubed, cubing a number that's been rounded off, well, whatever the round off error is, it gets magnified, of course. So you may have come up with slightly different answers in the hundredths column, depending on whether you used the pi button and whether you carried this through or rewrote it this way. What about the next part? 3 tennis balls in the container think we probably could have figured that one out on our own. Find the amount of space within a cylinder not taken up by the tennis balls. Oh, okay. That would be like wasted space, I guess. Well, what is the volume of the container? Well, for a cylinder, it's just the base, remember pi r squared, times the height. And they gave us all that stuff, I think. Yeah, they gave us the radius, they gave us the height, so this is easy. So if we just take our volume for the formula for the volume of the cylinder, it's the area of the circle times the height. Pi r squared times h, which is 55.38. Now we take our volume for the tennis balls, multiply it by 3, because there are 3 tennis balls, and you get 25.92. So the space left over in this cylinder, the space not occupied by a tennis ball, is 29.46. If you look at this, you get almost 26 cubic centimeters. I think that's in centimeters. Oh, pardon me, inches. Oh, okay. 26 cubic inches. And the space left over is 29.5 cubic inches, which means there is more wasted space than used space. And this was, again, seems to me a pretty easy problem. The biggest problems involving spheres are remembering the 2 formulas. 4 pi r squared for the surface, and 4/3 pi r cubed for the volume. And then, of course, you had to remember all your previous formulas. That's the trick to most of these practical problems involving area and volume. You have to remember a lot of your previous formulas to work them right. Okay, here's another one where they're just being a little bit tricky. You're going to have to find some of the parameters you need with the information given. For instance, the circumference. Well, the circumference, remember, for a sphere has the same formula as a circle with the same radius. So we have the 2 pi r equals 27. Pardon me, 27 pi. That's much easier. So we can divide through by pi and get that r equals 27 over 2. 13.5. Why would we want to know that? Well, they ask us to calculate the volume of the balloon. For that, we're going to need r. And the volume, of course, 4/3 pi r cubed. Well, if we do this, we've found that r is 13.5. So, to get the volume, 4/3 pi r cubed, when I use 3.14 for pi, I get this answer. When I use the pi button, I get this answer. So, once again, if you get slight differences in your answer, well, when you're using pi and approximations, round off, you're going to end up with some differences, although 6 units in this column here, or closer to 5, I suppose. That seems like a lot to me. But that's the way it goes. If you use 3.14, you get this one. If you used your pi button, you would have gotten this one. The pi button is probably more accurate, so we could stick with this if we need it. So we'll just stick it up in there, 10.306. What about this? Suppose you double the radius by increasing the air in the balloon. Well, come on, we've done things like this before. This is easy. The original volume is 4/3 pi r cubed. That's, say, v. What about v prime, where we've doubled the radius? How about 4/3 pi 2r cubed? Well, is that? 2 cubed is 8. So we could write this as 8 times, 4/3 pi times r cubed. Because when we cube these two, we get 8r cubed. We pull the 8 out, put it in front here. Well, that's just 8 times our original formula, isn't it? And that makes sense. Remember when we doubled one side of a square, we squared the area. We doubled the perimeter, but we squared the area, because area is units squared. Volume is units cubed. When we double them, well, we take 2 cubed. So when we double the radius, if our scale factor is 2 for the radius, our factor for the volume is 8. And I think that's all they asked. First they wanted us to do it with real numbers. I don't really see the point in that, to tell you the truth. I would much prefer to just stick it in general terms and immediately spot the relationship. So it seemed to me that the extended response question was actually easier and shorter than the previous short response question. I guess it depends on how you look at it. This is actually pretty simple. For this first part, we just had to find the radius. That was real easy. We used that to find the volume. And then, for some reason, they wanted us to use actual numbers to see what the difference in the volume was. But I think you're sophisticated enough by now to understand that all we have to do is put a 2r in here for the r and immediately find out what the difference is between the two. And the difference is you multiply 1 by 8. That is, the volume increases by 8 when the radius increases by 2. Here we have a question about the Earth torrid zone. If you're not familiar with the torrid zone, that's where all those torrid movies come from. It's a little strip right around the middle of the Earth between Tropic of Cancer and Tropic of Capricorn. Well, none of that really matters. This is all just words, and in mathematics the words aren't that big a deal. All that's important is that we have a strip. We have to know the radius of the strip. We're going to treat it as the lateral surface of a cylinder. So all we need to know is the radius and the height. They gave us the height, and they're about to give us the radius of the Earth. Okay, there it is right there. And what they want to know is, what's the surface area of this band, which apparently is centered at the equator, is 3,250 miles wide, and has a radius of 3,963 miles. You could call this the Mike Jones zone if you wanted to. I don't see what difference it would make. It's the numbers that matter here. So let's set this up. What would it be? Well, for the lateral surface of a cylinder, we just forget the top and the bottom. We don't need the pi r squared part for the two ends of the cylinder. We just need the lateral surface, kind of like the body of the cylinder. And that would be the circumference, 2 pi r. So there's just a whole lot of numbers to this one, but it's not really all that tough. To get this band, we use our 2 pi r times h, which is 2 pi times this big number they gave us here for the radius of the Earth, and this other big number, which is the width of the band. And it turns out to be this other big number here, 80,095. You can read it. Now, what they want to know is if a meteorite is likely to hit anywhere, equally likely to hit anywhere, and estimate the probability that it will land in this band here. And keep in mind this idea of equally likely to hit anywhere. I'm not sure that's really true. There's a lot of magnetic fields at the poles of the Earth, and incoming particles get caught up in those magnetic fields and tend to get thrown, I think, more towards the equator and not up here. But I could be wrong about that. I think that's a big big reason that there's such a thing as a northern lights. So the incoming particles get caught up in the electric field as they're hitting the Earth's surface. They're burning up, but not moving in a straight line. And I could be entirely wrong about that. For now, let's pretend that every part of the Earth is equally likely to get hit by a meteorite. If you're in this zone, what's the probability that one lands on your head? Well, you would just take the band here that you're concerned about and divide that by the entire surface. So you would get the surface of the torrid zone divided by the entire surface of, let's just say, big E for Earth. And if you take this number and divide it by this great big number, you will get 0.41, or 41%. Again, this was really a pretty easy problem. We just had to remember our formula for this band here, the lateral surface of a cylinder. Then we had to remember surface area for a given radius. Then we had to remember how to take probabilities. When everything is equally likely, it's just the area of the part you're concerned with divided by the entire possible area. In this case, the area of the torrid zone divided by the entire Earth's surface. Well, that's about it.